Every rocket that has ever left Earth has fought the same losing battle. Not against distance, not against the vacuum of space, against something far more stubborn, a mathematical trap built into the very physics of propulsion, one that gets worse the harder you try to escape it. We like to imagine a future of gleaming starships, effortlessly lifting off and carrying humanity to new worlds. But the honest, unglamorous truth is this: with the physics we currently understand, permanently escaping Earth, not just visiting space, but truly leaving for good in any meaningful numbers, might be one of the hardest problems humanity has ever faced. Today, we're going to look at why. Welcome back to the channel, where we break down the universe's toughest, most surprising problems in plain language, in the spirit of Brian Greene, where physics becomes a story instead of a lecture. If you're new here, this is exactly the kind of question we love digging into. Not just, can we do this, but what does the actual math say about whether we ever really can? Before we start, if you want more videos like this, hit subscribe. Stay until the end, because the deeper we go, the more this problem starts to look less like an engineering challenge and more like a fundamental law of nature working against us. And if you're enjoying this, please hit like and share it with someone who'd find this fascinating. Let's get into it. To leave Earth's gravity entirely without any further propulsion, an object needs to reach escape velocity, about 2 kilometers per second, or roughly 25,000 miles per hour. That number alone doesn't sound impossible. Rockets achieve it every year, but escape velocity only tells part of the story. It assumes you're not fighting air resistance, and it doesn't account for the fact that you need to carry your own propulsion, and the fuel for that propulsion, and the fuel to carry that fuel all the way up with you. This is where the real problem begins. A problem so persistent that rocket scientists have a specific, almost resigned name for it. In 1903, Russian scientist Konstantin Tsiolkovsky derived what's now called the rocket equation, the single most important and most brutal formula in spaceflight. It shows that the amount of fuel needed to reach a given speed increases exponentially, not linearly, with that speed. Double your desired speed and you don't need twice the fuel. You might need many times more because all that extra fuel itself has mass, and that mass needs its own fuel to move. Physicist and rocket scientist Robert Heinlein once called this the tyranny of the rocket equation. And it's not an exaggeration. It's the reason a rocket capable of reaching orbit is almost entirely fueled by mass, often over 90%, with the actual payload, the part that does anything useful, making up a tiny fraction of the total. This single equation is arguably the biggest reason spaceflight remains as difficult, expensive, and rare as it is, over 60 years after the first satellite reached orbit. Let's put real numbers to this. NASA's Saturn V rocket, which carried astronauts to the moon, weighed about 5 million pounds at launch. Of that, roughly 85% was fuel. The actual Apollo spacecraft that reached the moon weighed a small fraction of that total, and the tiny capsule that brought astronauts back to Earth was smaller still. Now scale this up. To reach Mars, spacecraft need significantly more fuel and much more complex trajectories, planning years in advance around the narrow windows when Earth and Mars align favorably. Because we don't yet have the propulsion technology to simply fly there directly, anytime we want. To leave the solar system entirely, as Voyager 1 and 2 have done, required using gravitational slingshots around other planets, essentially borrowing momentum from Jupiter and Saturn's gravity, because no rocket we've built could otherwise supply enough fuel to reach those speeds through propulsion alone. Chemical rockets, the kind that have powered every crewed mission in history, work by burning propellant and expelling the exhaust at high speed. But there's a hard physical limit to how fast that exhaust can go based on the chemical energy stored in the fuel itself. Even our most efficient chemical engines top out at an exhaust velocity of around 4 kilometers per second. Because of the exponential nature of the rocket equation, this puts a practical ceiling on what chemical rockets can ever achieve. Reaching even a modest fraction of the speed needed for efficient interplanetary travel, let alone interstellar travel, would require an amount of fuel that becomes physically absurd, often exceeding the mass of the rocket itself by factors of hundreds or thousands. This is why, despite over half a century of engineering refinement, chemical rockets today aren't dramatically more capable than the ones that flew Apollo missions in the 1960s. We've made them more reliable, more reusable, and cheaper, but the fundamental physics hasn't changed, and it can't. Even if we solve the fuel problem, escaping Earth means leaving behind something we rarely think about: our planet's protective magnetosphere, generated by Earth's molten iron core, which shields us from most of the sun's radiation and dangerous cosmic rays. Once outside this protection, in deep space or on the surface of Mars, which has no meaningful magnetic field of its own, astronauts face significantly higher exposure to radiation, increasing cancer risk and potentially causing damage to the central nervous system over long missions. NASA's own studies on astronauts who spent extended time on the International Space Station, which still sits inside much of Earth's magnetic protection, have documented measurable bone density loss, muscle atrophy, and vision changes from prolonged time in microgravity. A true interplanetary or interstellar journey lasting months, years, or generations would multiply these health risks dramatically, with no complete solution currently known. To put the scale of this problem into perspective, Mars, our closest potentially habitable planetary neighbor, is on average about 140 million miles away. Current chemical rocket technology gets a crewed mission there in roughly 7 to 9 months, one way, under ideal alignment. Proxima Centauri, the nearest star system beyond our own, is about 25 trillion miles away, roughly 270,000 times farther than Mars. Using the same chemical propulsion technology, that trip wouldn't take months. It would take, by most serious estimates, tens of thousands of years. This is the brutal scale difference between difficult and essentially impossible with our current technology. And it's why serious scientists distinguish sharply between the challenge of reaching Mars, which is merely extremely hard, and the challenge of reaching another star system, which current physics suggests may not be achievable by chemical propulsion at any reasonable scale, ever. Couldn't we just build bigger rockets with more fuel? Up to a point. But the exponential nature of the rocket equation means that past a certain size, adding more fuel adds so much mass that it barely improves your final speed, while making the rocket exponentially more expensive and complex to build and launch. What about refueling in space? This helps somewhat and is actively being developed, but it doesn't eliminate the fundamental problem, since all that fuel still has to be manufactured and launched from somewhere, usually still requiring the same energy-intensive process to get it off a planet's surface in the first place. Is this why we haven't sent humans past the moon in over 50 years? It's a major factor. The moon was reachable within the limits of 1,960 seconds, chemical rocket technology, and enormous national investment. Mars and beyond push those same limits much further, requiring either far more resources, far more time, or fundamentally different propulsion technology we don't yet fully have. One of the most promising alternatives to chemical rockets is nuclear thermal propulsion, which uses a nuclear reactor to heat propellant, often hydrogen, to extreme temperatures before expelling it, achieving roughly twice the exhaust velocity of the best chemical engines. NASA and DARPA have actively tested this technology, including a recent joint program aiming for an in-space demonstration. It could meaningfully cut travel time to Mars, potentially down to around 4 to 5 months instead of 7 to 9. But nuclear thermal propulsion still isn't nearly enough to make interstellar travel practical. Doubling your exhaust velocity helps, but it doesn't escape the exponential nature of the rocket equation. It moves the ceiling higher. It doesn't remove it. A more radical concept, nuclear pulse propulsion, studied in the 1950s to 60s under the name Project Orion, proposed detonating small nuclear bombs behind a spacecraft to push it forward. Calculations suggested this could theoretically reach a few percent of the speed of light, but the practical and political challenges of launching nuclear explosives from Earth's surface, along with fallout and treaty concerns, have kept this idea firmly in the realm of theory. Ion propulsion, already used successfully on missions like NASA's Dawn spacecraft, works by electrically accelerating charged particles to extremely high exhaust velocities, far higher than chemical rockets. The problem is thrust, Ion engines produce an incredibly small amount of force, comparable to the weight of a piece of paper resting in your hand, meaning they can't be used to launch anything off a planet's surface. Their advantage only shows up over long periods in space, where they can very gradually accelerate a spacecraft to high speeds over months or years, using far less fuel than a chemical rocket would need for the same final velocity. This makes ion drives excellent for certain deep space missions, but they don't solve the fundamental escape problem. You still need conventional rockets to get off Earth in the first place. And even the most advanced ion drives remain far too slow to make interstellar distances practical within a human lifetime. Further out on the technology curve are fusion propulsion and antimatter propulsion, both of which remain largely theoretical. Fusion, the same process that powers the sun, could theoretically provide exhaust velocities many times higher than chemical or nuclear thermal engines. Projects like Project Daedalus in the 1970s designed theoretical fusion-powered probes that could, on paper, reach nearby star systems within a human lifetime, but we still haven't achieved sustained, controllable nuclear fusion for power generation on Earth, let alone compact enough for a spacecraft. Antimatter propulsion offers the highest theoretical efficiency of any known method, since matter-antimatter annihilation converts mass directly into energy at nearly 100% efficiency. But producing antimatter is staggeringly expensive and slow. Current facilities produce only tiny amounts at a cost of billions of dollars per gram, making any antimatter-powered mission purely theoretical for the foreseeable future. Every one of these technologies pushes the ceiling higher than chemical rockets, but none of them eliminates the underlying exponential problem, and none exist today in a form ready for practical use. Suppose somehow propulsion technology advances dramatically. There's still a second, arguably harder problem. The human body itself may not be built for long-term life beyond Earth. Extended time in microgravity causes measurable bone density loss. Astronauts can lose up to 1 to 2% of bone mass per month without intensive countermeasures, a rate far exceeding age-related bone loss on Earth. Muscle atrophy, cardiovascular deconditioning, and vision changes caused by fluid shifts in zero gravity have all been well documented on long-duration space station missions. Radiation exposure beyond Earth's magnetosphere significantly raises cancer risk and may cause long-term neurological effects, based on animal studies and limited human data. And there are unresolved questions about human reproduction in space or reduced gravity. We simply don't yet know whether humans could safely conceive, carry, and raise healthy children in Mars gravity, about 38% of Earth's, or in zero gravity at all, since no controlled studies have ever been possible. This means that even a perfect propulsion solution wouldn't automatically make long-term human settlement beyond Earth viable. It would only get us there. Surviving, thriving, and reproducing there is a separate, still largely unsolved problem. Beyond biology, there's a psychological dimension. Isolation, confinement, and separation from Earth for years or generations creates significant mental health challenges, something NASA and other space agencies actively study through simulated long-duration missions on Earth, like the High Seas Project in Hawaii. For any large-scale permanent settlement, let alone a generation ship traveling for centuries toward another star, maintaining a functional, stable society in an enclosed, resource-limited environment presents challenges we've never had to solve at scale. Small, isolated human groups throughout history have faced serious difficulties with limited genetic diversity, social cohesion, and resource management, even with the entire rest of Earth available for support. A truly isolated off-world settlement would face all of these challenges simultaneously, with no possibility of outside help. Putting all of this together, meaningfully escaping Earth, not a single mission, but a genuine self-sustaining human presence elsewhere, would require solving several extraordinarily difficult problems simultaneously, a propulsion breakthrough that fundamentally exceeds anything we currently have working at. Scale, radiation shielding effective enough for years-long exposure, a reliable solution to the biological effects of reduced or zero gravity, a closed-loop life support system capable of functioning indefinitely without resupply, and a stable, self-sufficient society capable of enduring the isolation involved. Each of these individually represents one of the hardest open problems in its respective field. Solving all of them together at the same time is why serious aerospace engineers and scientists tend to describe interplanetary settlement as extremely difficult, but may be possible within centuries, while interstellar settlement remains, for now, firmly in the realm of not currently possible with any known physics. So is escaping Earth truly impossible? Not necessarily forever, but the honest answer, based on the physics and biology we currently understand, is that it's vastly harder than popular imagination usually suggests. It's not simply a matter of building bigger rockets or waiting for slightly better technology. It requires overturning fundamental limitations in propulsion physics, human biology, and social sustainability, all at once. Maybe that's the real sobering lesson hidden in the rocket equation. Earth isn't just our home by circumstance. It might be for the foreseeable future, essentially the only place complex human life can actually survive, which makes understanding and protecting this one planet more important than any dream of leaving it behind. So that's why escaping Earth truly, permanently, at any meaningful scale, might remain one of the hardest problems humanity has ever faced. Not because we haven't tried hard enough, but because the physics itself keeps pushing back. If you found this fascinating, please hit like, share it with someone who'd enjoy thinking about this. And if you haven't already, subscribe to the channel so you don't miss what we cover next. Let us know in the comments, do you think humanity will ever truly settle beyond Earth, or is our home planet the only place we'll ever really belong? I genuinely love to hear your thoughts. See you in the next video with a new question and a new mystery to explore. Take care.